Welcome back to our studies on distributed systems. We will talk about linearizable systems and strong consistency today. Just a disclaimer before we start, linearizability is a pretty abstract concept. For this video, we just want enough theory so that we can later talk about how to build linearizable systems and why it's important for system to be linearizable. So we begin by talking about inconsistency. Right. Inconsistency, let's go over an example here. We have a database cluster that has a single master and two followers. A user sends a write request to the master, and this is a single leader. If you recall from a couple videos ago, this is our single leader schema, right? The user sends a write request, and the cluster sends a OK back, indicating that the new value has been updated in our cluster. Okay. Now, if you recall, when a new value has been written to the cluster, this new value needs to be replicated in our follower nodes, right? So replication has to happen here and here, right? And of course, this takes time to complete. Time taken to complete. Right, this part is fairly straightforward. Now, let's say suddenly our current master drops offline. It dies, right? For whatever network reason, this suddenly dies. And replication is still happening. So that means our follower node still contains the old value on both of them until the replication is complete, right? So there's some time when the master update, and then there's some replication that happens before our follower can also update, right? And our user now, he sends a new request, a read request this time, and the read request has to either land on this node or this node, right? If it lands on any one of these nodes, it's going to return the old value because it hasn't, because the database cluster hasn't updated, right? So this is inconsistent. This is an inconsistent system. Our goal is to make our database cluster strongly consistent. So this is what we want to do in this video. Okay. And what we will define as strongly consistent is the following. We want to make the system appear as if there are only one copy of the data and all components, all operations are atomic. Okay. So what that means in our small example here is that if the whole database cluster appears to be one copy, okay, so if it appears to be one copy, that means if we successfully written to any one of the if we successfully written to the database cluster, any read following the write, right? Any read following the write. So this read here after the write should return us not the old value, but the new value. Okay. So let me read that again. We want to make the system appear as if there were only one copy, of the data, right? So if there's only one copy of the data, and we update that copy, and that update is returned as success, any subsequent read from any client should return that new copy of the data, right? So that's what it means by automate. Operations are atomic. It either succeeds or it fails, right? And formally, we define linearization as the following. Event 0, this means event 0, presides event 1 in the whole history if the response of event 0 precedes invocation of event 1 in history of H. Okay. And if I break this down a little bit, this simply means that if we have a timeline and there are two events, let's say this is event 1 or event 0, and this is event 1. There's a invocation endpoint and a response endpoint, and this is also invocation, and this is response, right? You see how each event has some duration, right? And we kick off the event by invoking, and we end the event by receiving the response. Okay. So what this is saying is that a linearized system have event 0 that precedes event 1 if the response of event 0 precedes the invocation of response 1 in history H. So what that means is the response is always before the invocation. Okay, if that's a little confusing, that's okay. We will talk more concretely about what all of these means, and hopefully by the end of the video, you all have a better idea. And if not, I'll provide more reference material for you to study if you're interested. Okay. So our linearizable system defines the consistency in CAP, right? Consistency, availability, and partitioning, right? That's our CAP theorem. Linearizable system defines the consistency parameter in the CAP theorem. And in a strongly consistent system, as soon as client A successfully completes a write, all clients reading from the database must see the value written. So this is just kind of the result of what we want in our system. This is the result that we want. Now let's take a look at this nonlinear system. This system is nonlinear. Let's take a look at its behavior and why we call it nonlinear. So this is taken from DDIA, Design Data Intensive Application, Chapter 9. And here, this example shows that in a soccer match, Germany scored, and our new score is Germany is 1 and Argentina is 0. Let me zoom in a little more here. Right. The referee updates the database by inserting the new value into the leader, and the leader now replicates across the follower, here and here. Imagine two users, Alice and Bob, now tries to read from the database. If Alice reads from follower 1, okay, follower 1 updated here, and Alice is reading at this time, Alice is going to get the result, Germany has won the World Cup, okay? But if Bob sends a request and it lands on follower 2, which is here, and follower 2 has not yet successfully updated the scoreboard, right? Then Bob is going to see the old value, and he's going to say, "Oh, wait, no, they're actually still playing. It's 0-0." Okay, so there's inconsistency between Alice and Bob. You see how Alice saw the final score before Bob did, and yet Bob is still seeing the old value. This is the new value that Alice saw. So this system is nonlinear, right? The return result is not linear because it's returning old result at a later time when we've already seen the new result. Okay, and let's take a look at example here. We have 3 clients reading and writing to this database. Imagine we have a database that looks like this, right? We still have single master. Let's write it here. We have a single master, and let's say we have 2 followers. Okay, follower, and master. Client A sends a read request. Okay, let's say he sends a read request to this one. Okay, and returns 0. Client 2 also sends a read request. Let's say client 2's read request lands on the second node. At the same time, client C sends a write request, and we know write request, let's say, goes to the master, right? Write request goes to the master. What do you think client B would receive? Would it receive the old value? Should it receive 0? Or should it receive 1 where C has been writing? Right? Or should I receive 1? Because client B and client C are sending concurrent requests, and the request is landing on different node, we don't know what it could return. So the result of this read is 0 or 1. We don't know. Don't know. Right? And let's say client A is sending a read request. Right, client A sent a read request previously and got 0. Let's say he sent a new read request and he sends it to, let's say he sent it to the same node. Okay, let me erase the previous request. We know a 0 was returned. And he sends a new request, and it's reading, right? Here, this one. Should it get 0 or 1? Well, we don't know because write, you can see that C's write request is still happening, right? We don't know when it finishes, and this is another concurrent request, and so the result returned is either 0 or 1. It could be either one. We don't know. And the next request sent by B, right? You can see that C is still going on and hasn't finished. So again, we don't know if this new read is going to return 0 or 1. And until this write request has finished, right? Client A reads after this time when the write has finished, then it gets 1 back because write has completed, and we say write has completed when all the replicas have replicated this the new value. Okay. So this is a nonlinear system because we don't know what value we're going to get. This is also nonlinear. And you can see why this is important because if you're a database, if you're an application developer and you're trying to read some value and you can't guarantee that you're going to get the right one or the wrong one, there's how do you even design your application? Now let's discuss how we will make our system linearizable. We make our system linearizable by adding the following condition. After any read returns the new value, all following reads must also return the new value. This is what we want. We want to add this condition to make our system linearizable. Formally, our linear systems are non-blocking and equivalent to a legal sequential computation. This is our first property, property 1. This is the non-blocking property. Property 2 is the locality property. System is linearizable if all components are linearizable. Let's take a look. So in this example, we have two threads, thread A and thread B. They're both writing to some database. Let's say it's a map, right? Map.put. But as we're writing to the map, we acquire the lock and we lock the lock, right? And then we run put key and value. And then we sleep for 60 seconds. And after the sleep is done, we unlock the lock. And in thread B, at the same time, it tries to acquire the lock, but because we're sleeping on thread A with the lock acquired, this thread B gets completely blocked for 60 seconds. Right. So this is blocking. We can use lock to ensure linearization, but we block our threads. We block our progress. Okay. The first property says that our linearizable system are non-blocking. So while we can implement a linearizable system with locks, one of the property that we want is to have it be non-blocking. So how do we achieve this? So how do we implement our correctness in our system without blocking the system using lock? We introduce a new type of operation called compare and set. Sometimes can also be compare and swap. So it's either set or swap. Compare and set is a atomic instruction that checks the expected old value against the existing and set the new value if the check passes. Let's take a look at this example to see what it means. So here we have client A, B, and A, B, and D sending concurrent requests, right? These three requests are concurrent. Client B reads X, and during the read time, client D is writing X, and client A is also writing X. Right? Client A write X as 1, and client D write X as 0. Okay. In this example, we finish the write request first, and the write request, let's say X here, the database X equal to 0, and sometime later, the second write completes, and now X updates, and X is equal to 1. Okay. So in a linear system, B must also equal to 1. So it returns 1. And from what we mentioned above, anytime after we read the updated value, all subsequent read must also return that value, right? So client C sends a read request, and we must return 1. So this is the behavior of a linear system. Okay. Now we continue on. So client D finished writing here, client A finished writing here, and client B reads the request and returns 1. So all subsequent requests that's reading should also return 1, right? Our next operation, client B sends a compare and swap. Compare and swap, what compare and swap does is we first compare the value. This is the old, 1 is old, and 2 is the new value that we want to set. So we compare if the old value is equal to what the database currently contains. If it is, then we update the database with the new value, right? So here, database still has the value 1, and so when we compare 1 to 1, when we compare 1 to 1, we pass the if condition, and then we update the database current to database new. So now current this equals to 2. So here x is equal to 2, right? This is kind of straightforward to understand. And the next read request from client C also returns 2. Again, this is just the behavior of a linear system. We haven't talked about how we implement this yet. So this is just the behavior, right? And so here returns 2, and every other read that comes after this read and this read should both return 2, right? And okay, here's an operation. So casts 0 and 3, right? The client tries to, so we know that our x current is equal to 2, and our client C, or client D in this case, is trying to set 3. This is the new value that we're trying to set, but it thinks that the old value is 0. So it thinks that the old value is 0. Okay, so 0 does not equal to 2, and so we must return false, right? This makes sense. So here we get error, okay? Because the database should contain 2, but it checks against 0, and that's why it fails. Next operation, casts on 2 and 4. We just said x current is 2, and it compares 2 to 2. So now, because this condition passes, we're going to set x current is equal to 4. Okay. And on the next operation, right here, our customer reads from x because cast succeeded, and this operation happened right here, and it should return 4. So x is 4, read, this should also return 4. And in this case, this fails because if read now returns 2 all of a sudden, when it returned 4 here, this no longer is a linear system. So this, if this happens, this is no longer a linear system. So this is a non-linear system now, right? So this should not happen, right? This should not happen, and this if we're reading from the database, this should return 4, right? By what we define here. So again, a linear system is non-blocking. In our example here, none of the operation blocked, right? And we use compare and swap for atomic operation. And the system is linearizable if all components are linearizable. In this case, we haven't used this property because our system is just one component. Okay. And by our condition here, after any read, we should after any read return the new value. All following read must return the new value as well. And again, we use this example to kind of to showcase what this means. And again, this is just the behavior of a linear system. The behavior of a linear system.